Watching baseball and looking at numbers are meaningful, don't get me wrong, but have you ever seen what a hit looks like? Or have you ever seen what a really cool pitch looks like? From the pitcher's frame of reference, he throws the ball forward to the catcher. Check out the big screen. That's what his pitch looks like. You can see the pitcher throw the ball forward to the catcher. Where the graph stops is where the catcher is, 60 feet away. Let's watch the next pitch. Check out the big screen now. Wow, it went the same distance, but took a lot less time. That pitch was smoking. Here comes another one. Check it out. One more time to the big screen. Again, the ball went the same distance, but look how much more time it took. That was a really lazy looking pitch. The slope of the lines shows the speed of the ball. You can see that the second pitch was moving a lot faster than the third pitch because the slope is steeper. We can also see that the ball was moving away from the pitcher because the pitcher was standing at 0. Totally way cool from a picture. We have outlined on the board all the concepts needed to understand the construction and the interpretation of a DT graph. We know that the slope of a line on a DT graph shows velocity. And to calculate this velocity, it is the rate of change of distance. And we've seen how the velocity can show us the magnitude and the direction. So where do we go now? What do we do with this information that we learned from the DT graph? Well, we are able now to create another graph of velocity. We are learning about the velocity from this graph and can therefore create another graph, and we're going to call that a VT graph on velocity. But how do we get those points? We have taken the slope of this line, but to determine the slope of this line, we took the endpoints. Now, recalling from our lesson on velocity and acceleration, when you take the endpoints and use those in your calculation, you're determining an average velocity. We also mentioned in that lesson that there would be a more appropriate place to describe what's called instantaneous velocity, and that place is right here. I know what my average velocity is between those 2 points, but what is the velocity? What is the velocity at, say, t1, some instant in time? At that instant, I'm asking, what is my velocity at that point, at this point in time? Well, an instantaneous velocity is still determined by taking 2 points of displacement and their corresponding points in time. The only distinction between the two is where those points are taken. For average, you take the endpoints. For instantaneous, you take those slope points on either side of the instant in question and determine the slope of the line between those 2 points. Well, in comes a nifty time to talk about calculus terms. Now, we're not going anywhere near calculus beyond these definitions. Calculus is based around 2 concepts, taking the derivative and taking the integral. Now, derivative means slope of a line at an instant. And how we get that instant is by considering these 2 points and making them really, really, really close to each other. How do we make these 2 points close to each other? By shrinking the amount of time between the data, shrinking the amount of time between the times when we take those data points. And so in calculus terms, that's said as taking the limit. We let the limit of the distance between those 2 points approach 0. We don't let it equal 0. We let it approach 0 so that you still have 2 distinct points to take a difference between. And so taking the difference between 2 points that are really, really close to each other is called a derivative. Now, this line is intended to be the slope of a line at a given instant in time. And we call this line a tangent line. Now a tangent line is the slope of a line at exactly 1 point. The slope of a line at exactly 1 point. That's what a tangent line is. Now, in order to get a line that's exactly at this point in question right here at this instant, at that instant, these 2 points have to be really, really, really close to each other. Okay, great. Well, we're learning a bit more about what instantaneous velocity is. And let's go ahead and make that note. This note right here shows an instantaneous velocity. This slope of that line shows an instantaneous velocity. The slope of the whole thing shows the average velocity. Cool. Well, let's look at a couple more points. What is the instantaneous velocity, say, at T2? Well, once again, we take 2 small points really close to each other and determine the slope between those 2 points. Let's go one more. Call it T3. At T3, what is the slope of the line at that instant? So we take 2 points and determine the slope of that line. Well, check it out. If we are to visually look at these 3 tangent lines, you see that the slope of the line remains constant. Well, if the slope of a line on a dt graph shows velocity and the slope remains constant in time, we are saying that the object has constant positive velocity. So that is the data that we can take to the next graph and construct what's called a VT graph. So let's go ahead and construct a VT graph with this information.